as a part of applied physics course. I, Dr. Surya, Faculty of Physics from Institute of Aeronautical Engineering, Dundigal, Hyderabad. So today we are going to discuss the module 1 of applied physics course, that is quantum mechanics, right? So there are different modules in this applied physics course. First one is the quantum mechanics one, module 1, and module 2 is introduction to solids and semiconductor devices, and third module is semiconductor devices, and fourth module is this one. What is that? Fourth module is what is that? Clashes equations. That is solids, and the fifth unit is lasers and fiber optics. Okay, so these are the different units of quantum physics of model of this particular module. Okay, so the first part is the quantum mechanics. So let us see what are the contents in the quantum mechanics. So the contents in the quantum mechanics are introduction to quantum physics, de Broglie's hypothesis, wave particle duality, Davison and Germer experiment, time independent Schrodinger equation for wave function, and we need to understand what is the physical significance of the wave function, and other one is, and the last content of this module 1 is Schrodinger equation for one-dimensional problems. Schrodinger equation for one-dimensional problem. So in that we have an application called particle in a box. So right. So these are the different contents that are available in the module 1 course. So if you come to the introduction to quantum physics, right? So what are the basic what is the basic phenomena? What is the basic phenomena? So what are the reasons for the quantum physics? We know in physics we have different we have different branches. So we have Newton mechanics, we have quantum mechanics, we have nuclear physics, we have atomic and molecular physics, we have statistical physics, we have different types of physics, right? So out of this physics, so we need to start the quantum physics, right? So for every beginners, for beginners in quantum physics, we need to understand what are the reasons for the existence of quantum physics, right? What are the basic reasons for the existence of quantum physics, right? So what are the reasons why quantum physics has been existed? So the existence of quantum physics, the quantum physics was existed in the sense, it means that there are some failures. There are some failures in previous physics. Right? There are some failures in other physics. So the failures in other physics are something assumed to be the Newton physics. So there are certain failures of Newton physics, right? So there are certain failures in Newton physics. So is the reason the existence of quantum physics or quantum mechanics. So if you come to the first part, that is the introductory part to quantum physics. So quantum physics, so we need to understand the basic reasons for the failure of classical physics and the reasons for the existence of quantum physics, right? So introduction, so that is what we are telling. So an introduction is the failure of classical physics and the advent of quantum mechanics. That means classical physics or classical mechanics was failed at one extent. So at certain regions or at certain parts, the classical physics was failed, and the reason came the existence of quantum physics. So that is what we are telling, the failure of classical physics and advent of quantum mechanics. So there are so many reasons. For the failure of classical physics and existence of quantum mechanics. So that's what in the first part of the 20th century was a challenging period for classical physics, right? So the first part of 20th century was a challenging period for classical physics. That means there are certain phenomena, or there are certain properties, or there are certain cases where the classical physics was unable to explain some properties, certain phenomena, right? So that's why it became a challenging period for classical mechanics or classical physics, right? So this classical physics, there are certain contents, or there are certain topics, there are certain features where the classical physics was unsuccessful in explaining them. So is the reason the quantum mechanics has come into existence. That's what we are telling. The first part of the 20th century was a challenging period for classical physics. So that means the classical physics in the starting part of 20th century, there are certain cases where the classical physics was unsuccessful. It was unsuccessful in explaining certain topics, right? So those topics that were unsuccessful in explaining by classical physics were overcome, were successfully explained. By whom? Were successfully explained by quantum physics. Right? So quantum mechanics has emerged during that time due to the failure of classical physics. That's why quantum mechanics has played a significant role in the development of various disciplines of physics. That's what we are telling. Quantum mechanics has played a significant role in the development of various disciplines of physics. So the key role played by quantum mechanics. So the key role played by quantum mechanics in the sense there were certain failures that were examined. That were examined by classical physics. So classical physics was unable to explain certain topics. So these classical physics topics which were unsuccessful were explained by quantum mechanics. That's why quantum mechanics has played a significant role in the development of various disciplines of physics. So basically, what is this quantum mechanics is? Quantum mechanics is a fundamental theory in physics. Quantum mechanics is a fundamental theory in physics. So that is what we are telling. Quantum mechanics is a fundamental theory in physics that provides a description of physical properties of nature at the scale of atoms and subatomic particles. Right. So that's what quantum mechanics is, a fundamental theory in physics. Quantum mechanics is a fundamental theory in physics that provides a description of the physical properties of nature. So what are the physical properties of nature that we will discuss? What are the physical properties of nature? Because while we explain the physical properties, these physical properties were unsuccessfully explained by whom? By classical physics. Right. So classical physics was unsuccessful in explaining some physical properties. Not only some physical properties, it was unable to explain certain basic parameters. Right. So that we will see what are the at atomic scale. That is what we are telling. Quantum mechanics is a fundamental theory in physics that provides a description of the physical properties of nature. So what are the physical properties of nature? Physical properties of nature are, we'll see what are those physical properties of nature, right? So physical properties of nature like black body radiation, right? Quantum theory of radiation, right? Compton theory, photoelectric effects. So these are all the things that comes in the physical properties of nature. That's why quantum mechanics is a fundamental theory in physics that provides a description of the physical properties of nature at the scale of atoms, at the atomic scale and the subatomic scale. At the atomic scale and at the subatomic scale. Right? So that means classical physics was unsuccessful in explaining certain features that are related to physical properties of nature at the scale of atoms and subatomic particles. That means classical physics was unable to explain certain phenomena. So those phenomena where classical physics was unsuccessful is this classical physics was unsuccessful in explaining about the black body radiation, which is a physical property of nature. Black body radiation, right? Not only this black body radiation, right? So this was all black body radiation. Right? And also it was unsuccessful in explaining the scale of atoms, that is stability of the atom at the atomic scale. Right? And third one, it is also unable to explain, the classical physics was also unable to explain what is photoelectric effect developed by Einstein. Which was developed by Einstein. So these are these three. So there are so many reasons, right? So there are so many reasons at the at the course level, there are so many reasons why, the reasons for the existence of quantum mechanics is the failure of classical physics. So the classical physics has failed to explain certain features at the atomic scale, and also it could also, it also provided some, provides a description of the physical properties of nature. So physical properties of nature, in the sense, as I told you, so those are at physical nature, right? Physical nature, like black body radiation. It could also not explain what is the stability of the atom, photoelectric effect, Compton effect, right? At physical properties, if you see some more physical properties, is classical physics was unable to explain what is interference, diffraction, polarization at the optical levels. So these are so many reasons where the classical physics was unable to explain, and unable to explain, and the quantum mechanics has been existed. Quantum mechanics has existed. That's why we told quantum mechanics has played a significant role in the development of various disciplines of physics. Right? And at the same time, we are telling quantum mechanics is a fundamental theory in physics that provides a description of the physical properties of nature at the atomic scale, and subatomic scale. Right? So if you need to understand what is an atom, what we know that what is an atom is. Atom is nothing but the smallest unit of ordinary matter which exists in three states, of course, in four states: solids, liquids, gases, and not also in the plasmic state. Right, so that's why an atom is the smallest unit of ordinary matter that forms a chemical element, right? So, and the atoms are extremely small, as we know that atoms are extremely small, right? Extremely small. Typically, around the dimension of the atom is approximated to be 100 picometers. It's approximated to be 100 picometers across, 100 picometers across, right? So that's why atom is the smallest unit of ordinary matter that forms a chemical element. Atoms are extremely small, typically around 100 picometers in 100 picometers across, right? So in physical sciences, right? Because in physical sciences, so these subatomic particles are smaller than atoms. Subatomic particles are smaller than atoms, right? Subatomic particles are smaller than atoms. They can be composite particles. Composite particle means particles such as neutrons and protons, are elementary particles. Elementary particles, electron, protons, and neutrons, right? So that's what in physical sciences, subatomic particles are smaller than atoms. They can be composite particles such as a neutron and proton, or atomic, or at elementary particles, electron, proton, and neutron, right? So that's why an atom is the smallest, because what the reason behind discussing the atom part is, we are telling that quantum mechanics is a fundamental theory in physics that provides a description of the physical properties of nature at the scale of atoms and subatomic particles. At a scale of atoms, right? So when we speak about the scale of atoms, we need to understand what is an atom is. What is an atom? Atom is the smallest unit of ordinary matter that forms a chemical element. The dimensions of atoms are approximately assumed to be 100 picometers across, right? So the atoms are extremely small, typically around 100 picometers, right? In physical science, when we study the science in physics, when we want to study, that is what in physical science, the subatomic particles are smaller than atoms. Subatomic particles are smaller than atoms. They can be composite particles such as neutrons and protons, or elementary particles, right? So this is what the introductory part. This is not the introductory part. It is continued to some more, right? So that's what we are telling: the failure of classical physics and the advent of quantum mechanics. And first quarter of the 20th century. That's why we told the first part of the 20th century was a challenging period for classical physics, and quantum mechanics had played a significant role in the development of various disciplines of physics. Disciplines of physics in the sense, when we speak about the nuclear physics, when we speak about the molecular physics, when we speak about the statistical physics, when we speak about the particle physics, for every part of physics which are studied at the macroscopic and microscopic nature, quantum physics becomes a major, quantum mechanics plays a significant role, right? Because that's what quantum mechanics are fundamental, that provides the description, because that's what we told, quantum theory is a fundamental theory that in physics that provides a description. It gives a description of physical properties of nature. It talks about some of the properties that are shown to be in nature at the scale of atoms and subatomic particles, right? And also we need to understand. So quantum physics is the study of matter and energy at its most fundamental level. So it is the interactions. Quantum physics is the interaction between the matter and energy. So that's why we tell interaction of interaction between interaction between quantum physics is the interaction between matter and energy, right? So that's why quantum physics is the study of matter and energy at its most fundamental level. That means the interaction between matter and energy. Matter exists in three forms, of course in four forms. So that is in liquids, solids and gases. Solids, liquid, gases, and at the most plasmic state. So interaction of solids with energy, interaction of liquids with energy, interaction of matter, interaction of gases with energy, interaction of plasmic range or ionic state. So interaction between, that's why we are telling that quantum physics is a study of matter at the most energy levels, fundamental level. So quantum physics is the interaction of matter and energy, and this at its most fundamental level, right? So quanta, that is what quanta is, nothing but quanta behaves very differently to microscopic matter. So that's what quanta behave very differently to microscopic matter. So here we have two types. One is a microscopic, which we can be seen microscopic, and other is macroscopic. There is macroscopic state. Microscopic state is the state which can be seen through a naked eye. Macroscopic state is the state which cannot be seen through our naked eye. Rather, it is to be sensed, right? It is to be assumed. So that's why we tell quantum mechanics or the part of quanta behave very differently to macroscopic matter. So it behaves very differently to this particular macroscopic state, right? So microscopic state in the sense which can be seen through a naked eye. So that can be seen through that analysis can be done by using the classical physics or classical mechanics. That's why. So quantum behaves very differently to macroscopic matter. Macroscopic matter in the sense, macroscopic state in the sense where we need to observe the sensation or the sensing phenomena, right? The sensing phenomena exists for macroscopic state. That's why quanta behaves very differently, right? Very differently. So this part of behavior for macroscopic matter can be observed for some particles, because macroscopic state will be existed for some particles, right? So quanta behave, that's what we tell, that quanta behave very differently to macroscopic matter. Here, the particles can behave like waves. Here, particles. So when we speak about the macroscopic nature, this macroscopic nature is to be intended for some particles, because particle behavior is to be understood when we speak about the macroscopic matter. And not only that, we are telling that quantum physics, it is the interaction between matter and energy. Matter and energy at its most fundamental level. When we study the quantum physics, as the interaction between matter and energy at its most fundamental level, then a property of quanta will be existing. This quanta will behave very differently for the macroscopic matter. So how this quanta behave very differently to macroscopic matter considers for some particles. Because quanta, we are telling that the property of quanta behaves very differently to macroscopic matter. Macroscopic matter in the sense, see, if you apply some pressure on a duster, on a sponge, the particles get compressed and the particles can get elongated. So this is what the macroscopic nature, rather only we can only observe, but we cannot physically seen through a naked eye. Right, so that is what we are telling, that quanta behave very differently to macroscopic matter. Here, particles can behave like waves because the quantum means we need to speak about the particles, particle nature, right? Particle behavior, right? So that's what we tell here. Particles can behave like waves, right? And waves behave as though they are particles. So that means there exists dual nature. Right? Here, particles behave as waves, here we observe particles will behave like waves, and waves behave as though they are particles. Right? Particles behave as waves and waves behave as though they are particles. That means there exists dual nature, right? So particles means we understand the particles like elementary particles like electrons, right? Electron or a material particle. Material particle will behave, the wave nature will behave, the material particle will behave as a wave, right? And waves at its level will behave as though it is a particle, right? So that's why here particles can behave as waves and waves behave as though they are particles. So the basic principle of quantum physics is that the energy comes in indivisible packets called quanta, right? Energy comes in the indivisible packets called quanta. So that is what we are telling, a central tenet. So that is central tenet in the sense that a basic principle of quantum physics is that energy comes in indivisible packets called quanta. That means energy is to be quantized. Here we tell that the basic principle of quantum physics that energy comes in the indivisible packets called quanta. That is what we speak about, the quantization of energy. We speak about the quantization of energy, right? So that is what a central tenet called basic principle of quantum physics is that energy comes in indivisible packets called quanta. Quanta is nothing but quantization of energy. So if you need to speak about the quantization of energy, fundamentally we need to study one more property of quantization in terms of charges, that is called the quantization of charge. Right? What do you mean by quantization of charge? So how the charge is quantized. As we have studied in our lower classes, we need to understand what is quantization of charge. Quantization of charge, that is what, as we've seen that energy is quantized, similarly charge is also to be quantized. Quantization of charge. Quantization of charge. So quantization of charge is an existence of charge in integral multiples of elementary charges. So quantization of charge is nothing but integral multiples of elementary charges. If you take E is the elementary charge and Q is the total charge. So total charge is an integral multiple of elementary charge. In the case how we define the quantization of charge is Q equals to NE, where Q is the total charge, which is an integral multiple of elementary charges, where n is an integer. Goes from n equal to 0, n equals to 1, 2, 3 and so on. Right? So Q equals to Ne. So that is what we speak about the quantization of charge. When we speak about the quantization of charge, we need also to speak about the quantization of energy. So energy is quantized. How the energy is quantized? Energy is getting quantized. That means existence of energy in terms of packets, in terms of bundles, in terms of bundles of energy. So instead of getting the energy as a continuous fashion, we need to get the energy in a quantum of energy. That means instead of getting the energy continuously, we need that energy is to be quantized. That means the energy to be quantized in the sense we need to explain that energy is existed in the form of integral multiples. That is what we write E equals to h nu, right? E equals to h nu, or we write E equals to n h nu. Okay. So E equals to NH, that means energy is quantized here. In the similarly way how we have studied the quantization of charge, Q equals to Ne, existence of elementary charge, the existence of charge in terms of elementary charges. Here also we need to study the quantization of energy as E equals to NH nu. That means energy is quantized here. NH nu, where N refers to the integer and H is a Planck's constant, nu is the frequency of the energy that is coming. The energy coming will be in the form of radiation. The energy. So that is what the radiation, the incoming solar radiation, instead of the radiation coming in continuous fashion, we discrete that particular radiation. In terms of some bundles of energy. Right. So when we discrete the energy levels in terms of some bundles of energy, then we tell that the energy is quantized, or the incoming solar radiation is quantized. That is what we take the bundles as a quanta, as a photon energy. That is what we are writing, E equals to NH nu, E equals to NH nu, right? E equals to NH nu, where N is an integer, H is a Planck's constant, and nu is the frequency. Frequency of what? Frequency of the radiation. Frequency of the radiation that is getting quantized. So this nu is further written as nu equals to c by lambda, where c is the velocity of light and lambda is the wavelength of the radiation. That is what we can tell that the energy is getting quantized. So this energy quantization has been existed from the charge, because when we speak about the charge, we're telling that, so that is what we are studying in the previous slide. So we need to study that the physical properties on the scale of atoms and subatomic particles, so small units, right? So when we speak of small units, so charge charge is also a fundamental property. That's why we need to study that quantization of charge as Q equals to Ne. Q equals to Ne in the sense Q equals to Ne, that is what exists in the charge in the integral multiples of elementary charges. So similarly, the energy getting quantized, that is V equals to NH nu, right? So that is what the central tenet, basic principle of quantum physics is, that energy comes out in indivisible packets called quanta. In physics, quanta, or the plural quantum, right? In physics, a quantum or a plural quanta is the minimum amount of any physical entity. That is what is the minimum amount of any physical entity or physical property involved in interaction between the energy and matter. So that is what we are telling, that quantum physics is a study of matter and energy at its fundamental level. So in physics, quanta, plural quantity, is a minimum amount of physical entity, that is physical property involved in interaction between energy and matter. So the energy contained in quantum field comes in integral multiples of some fundamental energy. So that is what the energy contained in quantum field comes in integral multiples of some fundamental energy. So that fundamental energy is what we are writing, E equals to, E equals to NH nu. So that means energy is quantized. Energy is quantized, right? So that means the energy contained in quantum field comes in integral multiples of some fundamental energy, where H nu is some fundamental energy and total energy E equals to NH nu. That's what similarly we have explained, that Q equals to elementary charge, Q equals to Ne. Ne is the elementary charge and Q is the total charge. So that energy is integral multiples of energy. That's why here we are telling the charge is quantized, here we are telling that energy is quantized, right? So that is what the energy contained in quantum field comes in integral multiples of some fundamental energy. So this energy containing in the energy contained in quantum field that comes in integral multiples of some fundamental energy is established due to the interaction between the energy and matter. That's why we tell quantum physics is the study of matter and energy at its most fundamental level, right? So that means here the physical entity is nothing but the physical property, right? It's a physical entity, the physical property, and quantum plural physical entity, right? So this physical entity is involved between the interaction between energy and matter. That's why quantum physics is a study of fundamental level. At the fundamental level, at the quantum physics at the fundamental level need to be understand the interaction between energy and the matter, right? So this is what something introduction behind the quantum physics, and we need to understand what are the challenges, because in the previous slides, we understood the earlier in the previous slide we studied one point, that the first quarter of 20th century was a challenging period for classical physics. So what was the challenging period? What were the reasons? What was the challenging? What are the gaps where the classical physics was unable to explain? So the first quarter of 20th century was challenging period for classical physics, as we told. So what are the changes? So what are the gaps, or what are the challenges we need to understand, right? So that's what we are speaking about this. That is a challenge of classical physics, that is mechanics of classical physics or classical mechanics. So as I told you, the challenge of classical physics in the sense, the gaps where the classical physics was unable to explain, which were overcome, which were successfully explained by quantum theory and Unsuccessful explanation by classical physics is that the properties like it is failed, the interference, it is failed that classical meanings, the challenge of classical physics, so the gaps existing for classical physics was the interference, diffraction and polarization. The interference, diffraction, polarization phenomena could only be explained by assuming that the light had a wave nature, right? So interference, diffraction, polarization phenomena could only be explained by assuming that light had a wave nature. But some other phenomena, but some other phenomena, but some other phenomena such as black body radiation, the photoelectric effect and Compton scattering defined, right? Define define the wave concept of electromagnetic radiation. Right, so that is what the diffraction, the interference, diffraction, and polarization. The interference, diffraction, and polarization phenomena could only be explained by assuming that light had a wave nature. But some other phenomena, such as black body radiation, right? Black body radiation, the photoelectric effect, and Compton scattering define the wave concept of electromagnetic radiation. Right. So these, as I told you, so these are some of the gaps, or these are sometimes some of the gaps where the classical physics was unable to explain. Right. So classical physics was unable to explain these particular phenomena, right? And these phenomena were successfully explained or successfully overcome by quantum physics, right? So if you see here, if you see the figures here, see, if you see a person climbing, this is if you see a classical physics, the person is trying to climb the hill by taking this particular rock, right? He's trying to climb the hill like this, right? So this is what the physically he can able to climb up the hill, right, and down the hill, right? So he need to take up the stone from the bottom to the top of the hill, right? Top of the hill, and tries to come down with the same rock and put it over here. Right, but so this is what classically we can see it. Because what we can see it classically, that this particular person will be able to move like this. But quantum physics is a phenomena of tunneling, right? So quantum physics is the property of tunneling. Quantum physics is a property of tunneling. Tunneling in the sense this particular rock can be tunneled. That means this acts for this rock. This acts as a barrier. So for this rock to move, to cross this barrier, this rock has to tunnel over this barrier, right? So that the particle reaches here. Instead of going the particle like this, it reaches here. So this is where the logic behind the quantum physics is existed, right? So that means quantum physics required some tunneling. Tunneling phenomena is a basic important property for quantum physics. So instead of taking the particle to the higher heights and coming down, it is physically shown. Classical physics means classically that particular person is trying to climb the hill, but quantum physics try to tunnel through the barrier. So that is what the classical physics, if you see here, this is what the classical mechanics and quantum mechanics is. So this particle need to cross this barrier. In order for the particle to cross this barrier, it needs, classical physics needs to go to this position. See, this is what the particle, in order for the particle to cross this barrier, this particle has to go to this position and comes down like this. But when we study about the quantum physics, this particular particle can tunnel into this barrier. That means there is certain region where that particular particle get obstructed. But quantum physics, when you apply some quantum physics to that particular case, then the particle will try to tunnel to the barrier and comes out as a particle, as initial the particle and final particle is. Right? So these are the certain challenges of classical physics, right? So that is what. So when we speak about the light having a wave nature, the interference, diffraction, polarization phenomena could only be explained by assuming that light had a wave nature. But some other phenomena like black body radiation, where we have seen that it provides a description of physical properties of nature. When we study about the physical properties of nature, but when we see the physical properties of nature, like black body radiation, the photoelectric effect, and Compton scattering define the wave concept of electromagnetic radiation. So these are the certain challenges where the classical physics was unable to explain. So these gaps or these challenges are overcome by taking the quantum mechanics under view. So this is what we understand between the classical physics, the introductory part between the classical physics and quantum physics, right? So if you see the black body radiation, because we told that some other phenomena such as black body radiation, the photoelectric effect and Compton scattering define the wave concept of electromagnetic radiation. If you see the black body radiation spectrum, the black body radiation spectrum was explained by Max Planck, who assumed that atoms of the walls of the black body acts as electromagnetic oscillators, harmonic oscillator. So an oscillator, we know that an oscillator can radiate energy only in the regions of quanta, right? So an oscillator can radiate energy only in quanta, that is, energy is to be quantized, because instead of getting the radiation continuously, this is our source of energy. If instead of getting the source of energy continuously, instead of getting the energy continuously, this energy need to be quantized. If you take the quantized energy, right, if you take the energy is quantized, so that means if you take the energy in terms of certain bundles of energy, we can tell that energy is quantized. That is what E equals to n h nu is what we can write. So that means an oscillator can radiate energy only in the quanta where with E equals n h nu, where n is a positive integer or 0. And nu is a frequency, as we told, nu is a frequency and h is a constant, which is what we define it as a Planck's constant, because E is energy, n is an integer, h is a Planck's constant, and nu is the frequency. So this new frequency is written as c by lambda, where c is the velocity of light, right, by wavelength of wavelength, right? So velocity of light is c equals to 3 into 10 power 8 meters per second, or 10 power 10 centimeters per second, right? So these are the certain units. So the remaining two phenomena in the sense, the remaining two phenomena like the photoelectric effect and Compton effect, right? So remaining two phenomena were explained by Einstein, right? The photoelectric effect were explained by Einstein. So that's what we wrote. So that's why we told that some other phenomena such as black body radiation and photoelectric effect. So these two phenomena, like the photoelectric effect and Compton effect, were explained by Einstein and Compton. By assuming that radiation itself, in particular, the remaining two phenomena were explained by Einstein and Compton by assuming that radiation itself in particular, light, consists of particles called photons. The remaining two phenomena were explained by Einstein and Compton by assuming that radiation itself in particular consists of particles. Radiation itself in particular, light in the form of radiation. We need to tell that light in the form of radiation. Light in the form of radiation consists of particles called photons. Light in the form of radiation consists of particles called photon, and each photon will constitute energy equals to nh nu. That means the light consisting of particles. So light in the form of radiation consists of particles called photons, and the energy of each photon is given by E equals to h nu. Right. So this is what we need to understand, some of the fundamental concepts of quantum theory, right? So the remaining two phenomena were explained by Einstein and Compton by assuming that assuming that radiation itself in the form particular light consists of particles called photons. Each photon possesses energy h nu. So we need to understand what is the Einstein photoelectric effect, and we also need to understand what is Compton effect. So that's what we'll see in the next classes. Right. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.